Okay, so last time we had started discussing the aspect of downsampling of 2D signals. In particular, we should be thinking about downsampling of images, and the setup we had proposed was we'll just focus on downsampling in each direction by some integer. So said we can downsample D1, D2, such that the output that comes up, f of D and m, that is simply equal to f of n d1 and m d2, which simply relates to you just downsample in one direction, and whatever you recover, you then downsample in the y direction. Now, the effect of downsampling on the frequencies of the input sequence is pretty much the same as the effect of downsampling that we saw when we do downsampling of 1D signals. The main effect that we saw was there is a stretching of the frequency axis when we do downsampling. So in the 1D case, we saw that there is only one frequency, and the frequency axis gets stretched by the integer that you downsample with. It's very similar to the in the 2D case. I won't go into the details, but I'll just say that if you want to figure out what is the Fourier transform of this downsampled sequence, it is related to the Fourier transform of the original sequence in the same way as the 1D case. In the 1D case, we had a scaling of the amplitude by 1 over the downsampling factor. In this case, we have downsampling in two directions, so we have 1 over d1, d2. And similarly, in the 1D case, we had, like we were using the symbol m in the 1D case, and we had m different versions of the original Fourier transform. In this case, since we are dealing with two dimensions, we will have two different copies. So j equal to 0 to d2 minus 1, and f of e to the j omega 1 minus 2 pi I over d1 omega 2 minus 2 pi j over d2. Even though the mathematical formula may seem daunting, the main thing that is happening, if you really want to think about it, you should focus on the copy of your Fourier transform that is centered around 0, 0. And if you understand what is happening to that copy, because the discrete Fourier transform is periodic, you can just replicate that everywhere. Okay? So we should really focus on what is happening with the copy that is centered around 0, 0. And if you focus on that, then we see that there are three things happening. Number one is that omega 1 axis is getting scaled by d1, okay, which is, so this scaling is represented through this factor omega 1 minus 2 pi I over d1. The second thing is that omega 2 axis is getting scaled by d2. And that is reflected through this expression. And the final thing is that the amplitude is getting scaled by 1 over d1, d2. 1 over d1 times d2. So if we think about our Fourier transform, we focus only on the main copy. Let's say that this is my Fourier transform support. I'm not drawing the amplitude, the magnitude version. and this is minus pi, this is pi in the omega 1 direction, this is pi and minus pi in the omega 2 direction. And let's say the amplitude of this thing, if I were to draw the 3D version, is A. Okay. Now let's define these endpoints. So this endpoint, let's define that to be little omega n1 0, and this endpoint to be 0 little omega n2. Okay. And of course, because of the periodicity, you will just have this thing tiled at 0, 2 pi, 2 pi, 2 pi, 2 pi, 0, and so forth. But let's just focus on what is happening with the copy at 0, 0, because then you can just replicate that and get your answer. Okay. So if you ask what happens, we just have scaling of the two axes and the amplitude scaling. So let's ask, what would that thing look like? If I look at what does the scaling do, this whole thing gets scaled by d1 in one direction and d2 in the other direction. In particular, this endpoint, so I'll get a stretching of this whole picture, right? And this endpoint now will become omega n1 d1 and 0. This endpoint will become 0 omega n2 d2. And similarly, every frequency in this central copy will get scaled by d1 in x direction, d2 in x direction, and the amplitude will be A over d1 d2. Okay. Now the question of whether this point goes beyond pi or not will depend upon simply how big is omega n1. So whether omega n1 d1 is less than or equal to pi, that will be a function of whether d1 is less than or equal to pi over omega n1. Okay. Similarly, whether omega n2 d2 is less than or equal to pi, that will be a function of whether d2 is less than or equal to pi over omega n2. Or equivalently, if you're in the x direction, your signal is band limited to pi by d1, and similarly in y direction, if your signal is band limited to pi by d2, then this whole stretching, even though you are stretching this thing will remain within the pi, minus pi to pi and minus pi to pi rectangle or square. Right? This whole thing will be captured within a square of minus pi to pi, as long as your signal is band limited to pi over d1 in the x direction and pi over d2 in the y direction. Otherwise, this thing will spill over into the next band, and when you now add the periodic copies, you will have overlap of those copies. So just like in the 1D case, you can do downsampling by a factor of d1 and d2 as long as your signal is band limited to pi over d1 in x direction, pi over d2 in the y direction. Otherwise, you will have aliasing. So aliasing will happen if omega n1 is greater than pi over d1 or omega n2 is greater than pi over d2. Okay. Now, to avoid aliasing, we can then, if you are in danger of getting aliasing, then what you should really be doing is, before downsampling, you should be having a low pass filter. You take your F and M, you have a low pass filter, and then you downsample by D1 and D2 to get F, D of NM. And the condition on this low pass filter should be that it should be an ideal low pass filter that cuts off every frequency above pi over D1 in one direction and pi over D2 in the other direction. So one type of that ideal low pass filter could be, for example, a complete box filter. So one ideal low pass filter could be filter is that you have this H of Nm, which has this Fourier transform H of e to the j omega 1 omega 2, which is equal to 1 as long as omega 1 is less than or equal to pi by d1 and omega 2 is less than or equal to pi by d2 and 0 otherwise in principal period. Of course, it's periodic, so it can't be 0 throughout. So this one will look like this will be one throughout these regions. It will look like a box. Another kind of an ideal low pass filter that people work with, you sometimes also see this cylindrical low pass filter, which is just a cylinder with radius of with the appropriate radius, so that it cuts off all the frequencies. Again, this is supposed to be in 2D. So if the frequencies are not bigger than pi over d1 and pi over d2, then you can just downsample. If the frequencies you are in danger of crossing that limit, then you need to low pass filter. Okay, that's the main thing you need to remember about downsampling. And finally, if this F and M, so let's say that there was f of xy, and you constructed that a sequence using f of nm, using sampling periods of x and y, and then you downsample. Okay, without the low pass filtering, if you downsample d1 and d2, and you get f tilde d fd of nm. Okay. So right now we have been talking about you get a discrete sequence and you low pass filter that discrete sequence. Right? The question is, what if that discrete sequence actually came by sampling a continuous signal? Well, in that case, this FDNM is just simply equivalent to resampling your original signal with a different period. Okay, so that is simply equal to f of, it will be f of n times d1x and m times d2y. Okay, so it is as if you are now sampling your signal with a period d1x and d2y. So if the sequence is coming from a continuous time signal, then the effect of downsampling is simply changing the sampling period with which you are sampling your signal. Okay? And it's exactly the same setup that you see in the 1D case too. Okay, that covers the detail that we are going to talk about as far as downsampling in images or 2D signals go. Now we'll move on to the upsampling part. All of these things can be derived in more mathematical detail using exactly the same tools and tricks that we have used earlier, with a few more sort of caveats that we have to be aware of, but there is nothing new to be learned from that discussion. So just like the downsampling case that we discussed earlier, upsampling in general can be performed in many different ways in a 2D case, but we'll work with the simplest version, which is that we upsample in one direction and then we upsample in the other direction. So what upsampling means is that you are given f of mn, and you first do an expansion operation just like we did in the 1D case. So you get d1, d2, which is an expansion operation, and we get this expanded sequence f of e mn, and then we pass it through a filter h of mn, which is ideally a low pass filter with a gain of, which is a function of d1 and d2, and then we get this fi mn, and this fi mn is called the upsampled version. So while in the downsampling case the filter is optional, you can still do downsampling without having the filter if your frequencies are not high enough. In the upsampling case, if you don't have the filter, then you are not going to end up with the upsampled version. You will just end up with the expanded version. So let's look at the two blocks. The expansion operation simply creates room for new values. It's similar to the case we did in 1D, which is that you expand your signal and put everything which is unknown right now as 0. So the expanded version simply looks like that you put in the value f of n over d1 m over d2 if n and m are multiples of d1 and d2. If n equal to k d1, m equal to k d2, some multiple where k equal to 0, plus, minus 1, and so forth, and 0 otherwise. Pictorially, what it means is that, let's take the example, you have, let's say, 4 pixels. So the idea of upsampling is that you take one sample, or in the case of image, you take 1 pixel and convert it into a d1 by d2 rectangle with zeros everywhere, except the location of the pixel. At the location of the pixel. Okay. So let's say if you were doing expansion by a factor of 2 in x direction and factor of 2 in y direction, what you essentially have is that this pixel, okay, gets expanded to, this is the original pixel, and now you have 4 additional pixels which we just label as 0 right now. We just create room for them. Right? Similarly, this pixel gets moved into this. This is the real value, and then there are all zeros. Similarly, this one, this is the real value, and then you have all zeros. And similarly, this one, you have real value and all zeros. So effectively, 4 pixels are turned into 16 pixels. So 4 pixels get moved to 4 by 4 equal to 16 pixels. You still have only 4 non-zero values. All the other values are 0. Okay? So that's the expansion part. You have essentially created a bigger room so that new values can come in. And now you need to interpolate those 0 values. You want to look at values of the pixel and you want to fill in that missing value. Right? That's the interpolation operation. And that's where the filter comes in. So if you look at that, what is the effects of the expansion operation only, not the upsampling. The expansion operation only, it's the same as the expansion operation as in the 1D case. In 1D, we looked at expansion and saw that filling in these additional zeros makes the frequencies compress by a factor of your expansion factor. It's the same case here. So expansion causes a compression of the frequency axis in particular the omega 1 axis that gets compressed to omega 1 over d1, and the omega 2 axis gets compressed to omega 2 over d2. So the Fourier transform of your expanded sequence e to the j omega 1 omega 2 looks like just this compressed version of your Fourier transform of the original sequence, omega 2 d2. Again, if this was your Fourier transform, it will simply get compressed. So if this was omega n1, 0, and this was 0 omega n2, okay, the first copy will come out to be, this one will become 0 omega n2 over d2, and this one will become omega n1 over d1, 0. Okay, and then there will be additional copies within even the minus pi to pi region, just like in the 1D case, and that's where the filtering operation comes in. It gets rid of those additional copies that we don't need. Okay, so after this expansion, we need to do interpolation through an interpolation filter, and the ideal interpolation filter is a low-pass filter with a gain of d1 times d2. So after the expansion, we have to do this low-pass filtering operation so that we can, so we take this expanded sequence f of e mn, and we pass it through a low-pass filter, which some people also call interpolation filter, which is a low-pass filter that has to throw out everything which is beyond. So this low-pass filter needs to filter all frequencies that are above pi by d1 in omega 1 direction and pi by d2 in omega 2 direction. So at some level, the interpolation filter, as far as its cutoff frequencies go, is almost like an anti-aliasing filter. Okay, you could use the same filter for both purposes. If you actually go and check out MATLAB's image resize command, it has just one implementation for both anti-aliasing and interpolation. So this low-pass filter has a cutoff omega 1c, omega 2c, c2, ideally at pi over d1 and pi over d2, okay, and you get FIMN. Now, many people will make this low-pass filter gain to be equal to d1, d2. While you will still get an interpolated signal, many people will make the gain of this low-pass filter d1, d2 because of the following reason. If you have the gain equal to d1, d2, and if your signal, if your sequence that you upsampled came from sampling of a continuous signal at sampling period xy, you get this f of mn. and then you do this upsampling by a factor of D1, D2 to get this expanded sequence Fe of Mn. And after that, if you do a low-pass filter with gain equal to D1, D2, and the cutoff omega C1, C2 equals pi over D1, pi over D2, if you do that, then it turns out that the interpolated signal is simply a resampling of your original continuous time signal that is simply given by f of n x over d1 my over d2. Okay. So you are now sampling it is as if you are sampling your sequence signal at a higher rate. Of course, if you don't do the gain, then the only thing that will change is that in that case, if the interpolation filter gain is not D1, D2, but if it's, let's say, 1, then the only thing that will change is that you will have simply a scaling. You will get Fi Mn will be just 1 over D1, D2 times F of Nx over D1 my over d2. Okay. But in many cases, you will see this gain being set equal to d1, d2 when you are doing interpolation. So the concepts here are very much like the 1D case that we saw earlier. It's doing downsampling. If the sequence comes from a continuous time signal, in 1D case, downsampling is nothing but resampling of your signal. If the signal comes from if your sequence comes from a continuous signal, upsampling is nothing but a resampling of your signal. Okay? It's the same concept in 2D or images or in higher dimensional settings. Now, you could use this, you can use combination of this upsampling and downsampling to actually create resampling and resizing of your images to any size that you like. So let's just briefly go over that aspect. You can resample or rescale of images through cascading of this upsampling and downsampling operation with the appropriate low pass filter. So we will work with the case where you are given an image and you want to scale its x pixel resolution and y pixel resolution by the same amount. If it's not the same amount, then the extension to that is not that difficult. Okay, so say you want to scale an image f of mn by a factor of, let's call it s. So if s equals to 1.2, that means you want to make your image bigger. You want a bigger image. And bigger, I mean in terms of resolution, not the size. Okay. If s, let's say, is 0.7, then you want a smaller image. And this scaling, we are saying, is in each direction. So if you have 1,000 pixels by 1,000 pixels image, and if you want to scale it by 0.7, you want a new image which is 700 by 700 pixels. And the way to do that, because 0.7, you can't, it doesn't relate to an explicit downsampling factor. Ideally, you want to downsample. If it was 0.5, then all you have to do is downsample by 2 and 2 in each direction. But 0.7 alone is not going to give you a downsampling. You can't use downsampling alone to convert it into a 0.7 ratio or a scale, convert it to a scale of 0.7 of the original size. Okay, so you really have to use upsampling and downsampling. Now the reason I'm saying upsampling and downsampling is because you don't want to do downsampling first and then upsampling, because you always have a danger of aliasing if you do downsampling first. Okay. Similarly, if you want to do 1.2, well, we can't do upsampling by a factor of 1.2. We can only do upsample by a factor of 2. So how do we obtain a new image which is 1.2 times the original image's resolution? Okay. So the idea is that you write the scale factor, write S as a rational number, or rather, since it is a rational number, you write it as a fraction of two numbers, as a fraction of two integers. So you say S equal to du over dd. Okay. For example, if for the case of 1.2, you can write S equal to 6 by 5. Or you can write S equal to 7 by 10 for 0.7. Okay. And this fraction basically tells you how much you upsample and how much you downsample. As the notation may even convey, what the goal is, you basically first upsample by du and then downsample by d little d in each direction. Okay. And the effect of this thing will be that you will achieve the scaling, because you first increase your, let's say if you're doing 1.2, you're going to increase the size of your image by a factor of 6, and then you decrease it by a factor of 5. The effective size will become 1.2 times the original size that you were working with. Okay. Similarly, if you are doing 0.7, you increase the size first by a factor of 7, then you decrease it by a factor of 10. So a general sampling, resampling, or resizing operation looks like the following. You first upsample du times, you upsample, expand, and then you have a low pass filter with the gain of du squared. So this is a low pass filter, and the cutoff is pi by du. Pi by du is the cutoff. So this is your upsampling, and after that you do downsampling, but just to prevent aliasing, because you don't know what the image will have. It may have frequencies that are above pi over dd, so you want to have an anti-aliasing filter first. So you have this anti-aliasing filter, which is again a low-pass filter. So anti-aliasing low-pass filter. The gain of this is 1, and the cutoff is pi over d sub d, pi over d sub d. And then you downsample by dd and d sub d. And at the end of the day, you get a new image of tilde mn, which is guaranteed to be related. If this FMN came from a continuous signal, then it's guaranteed to be just a resampling by a factor of 1.2 or 0.7. Okay. So this new image will have the scale related to du over dd in each direction. Now you can of course achieve some more saving in this operation by focusing on this block. And if you think about it, you have two low-pass filters in cascade, and the cascade of two low-pass filters is another low-pass filter. So this effectively is nothing but a low-pass filter with a gain of du squared and the cutoff is the smaller of the two cutoffs. So the cutoff is minimum of pi of du and pi of dd, comma, minimum of pi of du and pi of dd. Okay. So actually you can have just one low pass filter in this whole resizing operation. The cutoff of that low pass filter has to be determined by whether your upsampling factor is larger or your downsampling factor is larger. Okay. If upsampling factor is larger, then it will be pi over du. If downsampling factor is larger, then it will be pi over dd. Okay. So in the case of, for example, s equals to 6 over 5, right, the cutoff of this low pass filter will be pi by 6 and pi by 6. In the case of this rescaling by 0.7, your cutoff should be pi by 10 and pi by 10. So that's the general resampling or resizing in the case of images of signals that you can carry out by doing concatenation of upsampling and downsampling operations. Okay. There are, if you go into details of image processing, there are too many other aspects which we are not going to cover. Image processing is itself a very detailed topic. But the idea of this whole discussion is that most of the things that you learn in image processing, for example, are nothing but the extensions of 1D ideas, as long as you can wrap your head around the two-dimensional world. Okay. So we'll stop our discussion of two-dimensional signals or multi-dimensional sampling theory at this point. If this FMN came from sampling of some xy, and the sampling period was x and y in x and y direction, and no aliasing happened in this low pass filtering region, right? Everything was good. Then this f tilde mn can be written as a function of fmn, fxy. This f tilde mn is simply equal to then f of n dx over dux, comma m dx y over du. Okay, so it's effectively you are doing a resampling of your original image. But for that to happen, you must make sure that no aliasing is happening and all the conditions are satisfied. So we have finished the first part of this course, which was related to the sampling theory. And we are now going to move on to the second part of this course, which is transform domain. You can say digital signal processing or signal processing, but the implicit assumption is that we are dealing with discrete signals. Okay. So Of course, if you want to understand signal processing, the first main objective is we must understand how to sample these continuous signals and what is the relationship between the samples of continuous signals and the original continuous signals. We have done that. But once we have the discrete sequence, our goal is to do some processing on that sequence. That's what the purpose of digital signal processing primarily is. You are digitizing things because after digitization, you want to do efficient processing of that. Okay? So once we are given, let's say we are again going to go back to the 1D case, we are given xt and we sample it and we get back xn, and that is all good. But now once we obtain xn, now we want to process xn to achieve some objective. Now, some of this objective can be achieved through a simple filtering operation. You say xn is given, you pass it through an LTI system, a filter with an impulse response hn, and you get yn. So sometimes filtering is the answer to your processing problem. An example of that will be if you collect samples of some music, some song, and your goal is to, for example, increase the bass of your song. Well, that is just increasing the contribution of low frequencies in your signal. So that is just a filtering operation. You can take your samples, you can pass it through a filter, which increases the magnitude of the frequencies, low frequencies. You increase the bass of your signal, and that is done. You are done. But in some other cases, filtering alone or filtering itself is not sufficient for the processing goal that you are after. Okay? So, but some of the other processing or sometimes simply analysis happens best in a transform domain, and we'll see what that means, in a transform domain rather than through filtering. Okay. So one example of that is, for example, say you are given an image, given the image of a person, and of size, let's assume 10 megabytes. Okay? We are not talking about the resolution. Resolution is fixed. And you want to take this image and you want to reduce the storage size of this image. Now, when I say size, I don't mean resolution. I mean what amount of storage is that image taking inside your computer. Okay? So you want to reduce the size of this image from say 10 megabytes to perhaps 5 megabytes. But you don't want to either reduce the quality of the image. So without reducing the quality of the image too much perhaps, or the resolution. Resolution means the number of pixels you are dealing with. Okay? Now this problem falls under the category of compression. In modern signal processing, the best sort of way to do that is using this JPEG 2000 compression, which is based upon the idea of transform domain processing. This cannot happen through filtering operation. It's not a linear operation. Okay? So it's a nonlinear operation which you carry out in the transform domain. There are other examples of that. So this is not a filtering operation. Another example could be what is known as NMR spectroscopy. Which stands for nuclear magnetic resonance. So the idea in NMR spectroscopy is that you want to investigate the composition of materials, and by you I mean chemists or physicists or other people are interested, right? And they put these materials inside some sort of a very high magnetic radiation, and the nuclei absorb and radiate this EM radiation, and the emitted energy is at a specific resonance frequency, which is a function of the material that you are dealing with. So what happens in NMR is that every object, let's say you have some atom, you have some material, and it has different sort of atoms, and all of them, these atoms, emit EM radiation at certain resonance frequencies which are functions of the atom that you are dealing with, the strength of the magnetic field, and a number of other factors. But the main thing that happens is that outside this, what comes out is this thing called FID, or free induction delay, which is like a sinusoidal, a decaying sinusoidal waveform. Okay, and you can sample this waveform, which we know at what rate we should sample. But once we sample, so collect samples of this waveform. But once we collect these samples, we are really interested in this waveform has what kind of a frequency did this FID had. Because if you go and look at literature on NMR spectroscopy, you will see plots showing like this, okay? Certain peaks. And these peaks are related to the frequencies of these FID signals, and these peaks tell you, based upon their location, what kind of material is present inside, what kind of atoms are present inside a molecule, or other properties of the compound. So if you want to figure out which frequencies are present in Xn, again, that is not a filtering task. Okay, the question of identify main frequencies in Xn, that's the task of spectral analysis. Okay, that does not fall under the category of filtering. You can't do filtering to figure out which frequencies are present in there. Okay. So this falls under spectral analysis, the basic version of which can be done using perhaps DFT. And there are many other examples. Another example could be that you are interested in you are doing neuroimaging or you are recording neuron activity using electrodes, and you are trying to figure out which neuron fires and it causes which other neuron to fire and things like that, so that you can figure out how neurons in the brain are connected. Again, that's a task that you cannot simply do by doing filtering operation. Okay? Now, many of these tasks require more sophisticated tools than what we are going to cover, but a general phenomenon behind tackling these tasks is based upon the idea of transform domain processing, which is that you start with some sequence and you convert that sequence into another transform, and depending upon what kind of action you want to take on that sequence, there are good transforms available that people have figured out. So if you want to do the spectral analysis, maybe you should work with either DFT, the discrete Fourier transform, or short time Fourier transform. If you want to do compression, maybe you should work with either the discrete cosine transform or the wavelet transform, and so forth. Okay? So our goal here is just introduce basic concepts of transform domain signal processing, and perhaps do a few examples of some of the most commonly used transforms, which will include at least discrete Fourier transform, short time Fourier transform, and wavelet transform. Okay? And we may or may not end up doing too extensive kind of applications with them, but that could be then learned if you know the basic ideas behind these transforms. So the general principle that we will be doing in the transform domain signal processing is we are always going to work with finite duration sequences. In general, we will say that our sequence has length n, so it is not equal to 0 for n equal to 0, 1, up to n minus 1. Okay. So it's a length n sequence. We'll be calling it length n sequence. And oftentimes we will be writing this sequence as a vector in Rn. So we will be writing this as a vector x belonging to Rn, and the implicit assumption will be that the first sample is the first entry of this vector, the second sample is the second entry, and the last sample is the last entry. Okay? Because transform domain signal processing, even if you have not studied DFT or other transforms from the perspective of matrix vector multiplication, transform domain signal processing is really about just linear algebra. Okay? So we'll be writing that. We will be dealing with n-dimensional vectors. I will, without loss of generality, always be going back and forth between the sequence and the vector that corresponds to that sequence. And this discussion will be about one-dimensional sequences. Extensions to the multi-dimensional case is trivial in the sense of, when I say trivial, in the sense of what we have done earlier in the 2D case, and also because many of these transform domain ideas can be, from higher dimensions, can be mapped into one dimension. Okay, so we'll do that later, but this is the notation that I'll be using again and again, and it's important for you to make that connection. Finite dimensional sequence, finite length sequence, length n, which I'll sometimes write as a sequence, sometimes I'll write as a vector. Okay, so starting next class, we will give a more formal definition, which will be abstract, of what is a transform, what do we exactly mean by transform in this discrete domain, and then we'll move on to studying the first transform, which is the discrete Fourier transform. We'll end here.